Let us study about EMF induced in a rotating conductor in uniform magnetic field. Here you can see a uniform magnetic field exists in inward direction, and a straight rod PQ is rotating about its point P as axis of rotation with an angular speed omega. Here also you can see that this conductor is cutting magnetic flux in magnetic field, so there must be an EMF induced in it. Let's calculate the EMF by the two methods, one by motional EMF and other by Faraday's law. In this situation, as at every point of the rod the velocity is different, we consider at a distance x from center an element of width dx. The velocity of this element is v, and v we can write as x omega, where this element dx is revolving in a circle of radius x with the same angular speed omega. Now for this element, which is of width dx and velocity v, it is moving, we can write motional EMF induced in element dx is, this can be written as d, and the value will be bv dx, as we know motional EMF is bvl. So here in the element of width dx, motional EMF is bv dx. And by using the right hand palm rule, we can see that for this element dx, here its left end will be high potential and right end will be low potential. Or we can say this element dx will behave like a battery of EMF d, and several such batteries are connected in series between point P and Q. So here in this situation we can write total EMF induced across P and Q is, this can be written as EPQ, which is integration of D, and this can be given as integration of B. V we can write as x omega multiplied by dx within limits from 0 to L, as L is the length of this rod. So in this situation, this EMF induced across the ends PQ can be written as B omega as a constant, and x dx will be integrated as x square by 2 within limits from 0 to L. So here induced EMF across PQ is given as half B omega L square, which itself is a very important result, and in many cases this can also be used directly. And here by right hand palm rule we can directly say that point P will be the high potential end, and point Q in this situation will be the low potential end. Now on the next sheet I'll continue, and the same expression will calculate by using Faraday's law without using the direct result of motional EMF. Let's continue to understand the same analysis by using the Faraday's law, or there's an alternative analysis to get the same result. Here we can see as the conductor is rotating at an angular speed omega, in time dt we can see the conductor will reach a position where it is rotated by an angle d theta in time dt. So we can write the angle of rotation by conductor in time dt is, this can be written as d theta, of which the value will be omega dt, as the angular speed is omega. Now in this situation, this time the conductor has swept out this sector area, and we can directly write area of sector swept by conductor in time dt is, this area ds we can write as half r square d theta, and here we can substitute the value of d theta, it will be half r square omega dt. And if we calculate flux cut, magnetic flux cut in time dt by conductor is, this flux d phi we can write as b ds, and the area we already calculated, so this will be half b omega r square dt. And by Faraday's law we can directly write as EMF induced in conductor EPQ, which can be written as mod of d phi by dt, and here on substituting this, so we are getting it as half B omega R square. Here you can see the result is same, and which we have obtained by using Faraday's law, and in the previous sheet I have calculated the same expression, calculated the same result by using motional EMF result. So you must be careful while analyzing, as the most important thing here is the EMF induced in the rotating conductor given by half B omega R square.